In the last video, we looked at drawing some simple Lewis structures. Bond order refers to if there are single bonds, double bonds, or triple bonds within the molecule. It's really not anything to get your undies in a bundle about. Often you'd want to draw the Lewis structure first. If they ever said, hey, what's the bond order in blah, some molecule? Draw it first, because you really can't always predict if it's single bonds, double bonds, triple bonds by looking at the formula. So, after a while, you will kind of get used to common trends. You'll know that like hydrogen and halogens usually want to make single bonds. Oxygen is often interested in a single bond or a double bond. Could oxygen triple bond? Yes. Now that might not be my first thought, but that's why I would suggest drawing the structure first if they ever ask you the bond order. The nitrogen family likes to make triple bonds. The carbon family is usually looking to make 4 bonds. He could do single bonds, double bonds, triple bonds. He could do whatever he wants. So the whole term bond order really does just refer to whether the bond is single, double, triple. I would highly suggest drawing the Lewis structure first. Now, the other thing that we want to look at in this video is exceptions to the octet rule. So in the last one, we looked at Lewis structures that really did all follow the octet rule. We wanted to make sure we gave all atoms an octet using the correct amount of valence electrons. There are some atoms that don't need an octet. They might be stable with less than an octet, and we call them deficient octets. Now, don't overthink these things. BF3, boron. There's boron. He only has 3 valence electrons. And remember how we kind of draw them in a triangle? We try to show that if there are 3 areas of electrons on boron, they're going to repel. So we try to get them as far apart as possible, which is about 120-degree bond angles. That's all you got. You just have these 3 valence electrons. So let's add 3 fluorines with his 7. So we'll line up the singles so they match, right? Fluorine singles match up. Connect the dots or circle on whatever floats your boat. 6, 7. Connect the dots. Now don't freak out. Boron does not have an octet. He's only got 6 valence electrons on the outside. That's fine. He only had 3 to start with. Boron is okay with less than an octet. Don't overthink it. So common trends down at the bottom. Period 1 elements like hydrogen, I guess a hydrogen and helium, don't necessarily need an octet. They're really only looking to fill the first energy level with 2 electrons. So we call that the duet rule. And you're probably not going to deal with helium. So this really refers to hydrogen. Duh, and you knew that. Hydrogen only needs 2 valence electrons. Some other common deficients are beryllium and boron. Beryllium only has 2 valence electrons. We often kind of draw them opposite ends. So he usually only has 4 when he bonds. You might have like maybe hydrogens. Boop. Hydrogen, 1 valence electron. There we go. Connect the dots. Beryllium's only got 4 valence, and it's okay. That's common. So beryllium and boron often have deficient octets. As you keep going across, though, carbon, nitrogen, oxygen, fluorine, they will always have octets, no exceptions to the rule. Don't ever try to do anything funky with carbon or oxygen or anything like that. They need 8. But now as we get to the 3rd period or the 3rd energy level and beyond, you could have something called an extended octet. And again, don't overthink this. Normally, I would draw sulfur kind of like this. I'd have sulfur, He's got 6 valence electrons, so I normally go 2 pairs and 2 singles, right? Normally, I think about sulfur wanting 2 bonds. Let's pair up those single electrons, give them 8, which happens often. And then people look at this molecule, sulfur hexafluoride, and they're like, is that a typo? Like, are there supposed to be 2 fluorines? Where the heck are we going to put 6? Oh no, sulfur hexafluoride is super awesome and fun. And we'll talk about it in class. You know how helium makes your voice go real high? Sulfur hexafluoride is a gas, it's a real dense gas that makes your voice go low. So you kind of sound like Darth Vader. It's really cool. There really are 6 fluorines. So where are you going to put them? By the 6 valence electrons. So let's throw, whoopsie, that's not hydrogen, it's fluorine. 1 over here. And then we'll add the 7 valence electrons to fluorine. Link it up. We'll add 1 over here. Connect the dots. And now we're just going to bond all those extra electrons. There's 4 remaining. And normally this looks really stable. And this is a compound that exists. But in the case of sulfur hexafluoride, those pairs are going to break up and bond. Wow, that's cool. Okay, so there's 1 single and 3 pairs. Link them up. Fluorine, a single and 3 pairs. Just bond the 6th fluorine to the 6 valence electrons on sulfur. Boom, there it is. Sulfur hexafluoride. Don't overthink it. If there are 6 valence electrons and you got 6 fluorine, just throw them on the sulfur. Perfect. Sulfur has an extended octet. He's carrying more than 8. He's got 2, 4, 6, 8, 10, 12 valence electrons. And you know what? That's okay. In the 3rd period or the 3rd energy level and beyond, it's okay to have an extended octet because of this. D orbitals. When you have those big fat d orbitals, they can hold a lot of electrons. It's okay to carry an extended octet if you have d orbitals available. Oh, so now that's a good question that they're going to ask you on the AP test too. They might say, well, how come sulfur can take an extended octet but not oxygen? They're in the same family. They both have 6 valence electrons. Why can't oxygen do this? And we'd say, oh, well, oxygen's not in the 3rd period or the 3rd energy level. Oxygen doesn't have d orbitals available like sulfur does. So you can only use an extended octet when you're in the 3rd period or beyond, 3rd energy level and beyond. That's where you'll find the d orbitals. And that's where you can dump extra electrons. Cool, huh?